It's a pleasure to introduce our first speaker today and my collaborator. It's not Mohammed Abouzaid from Stanford, who will tell us about Bordism and resolution of singularities.
Okay, thank you, Lee. Just want to be back again in I'm going to talk about some words that Shaoyun Bai posted to the archive in December, I think. There's also, I think, mostly because there's a little bit of extra stuff about how it applies to symplectic topology, and that's going to work with Mark and I to make it a little bit older. So let me start with some kind of story, like what are we trying to do, why are we doing this? So if you just try to imagine the simplest possible situation, you realize that modular spaces of pseudo holomorphic curves in very good times or just compact stately complex manifolds. Now, if you're counting algebraic geometry, maybe you're surprised that I'm saying stately complex. Why are they not complex manifolds? It just has to do with the fact that if your complex structure is not integrable, then this is actually the best thing you can get. Anyway, so pardon?
That's stately complex to the
Okay, I can explain that. It'll show up in a second. So stately complex is a very soft notion. It means that the tangent bundle, after some stabilization, has a complex structure. After you have some but actually, I'll give some actual definitions because I'll do them more. But okay, so because the structure exists and it's essentially canonical, you could hope that this is where some kind of universal Gromov-Witten invariants live. And the idea is that it would refine both what we do, both the numbers that we count when we do quantum cohomology, and what we do when we do quantum K-theory. And as I right there, I think the first person to have this dream was probably me. Now, what I want to say is that if this dream were to take place, the person who's thought the most about it probably Giventhal, and you realize that when we do things in Gromov-Witten theory, we often involve degeneration. And in homology, when we degenerate the fundamental class, the number of elements just adds up. But in K-theory, already, if you take a normal crossing divisor and you smooth it, then then if you think of normal crossing divisor as given by each component is given by a line bundle, then the smoothing is basically given by the tensor product. And class in K-theory does not exactly add, topologically add, there's some kind of multiplicative correction. And if you were to instead do this in complex cobordism, then you would have to involve this kind of universal formal group law. And there would be some extremely complicated additional structure that Gromov-Witten theory would be formulated under. And formal group law is some kind of polynomial in two variables, x and y. We should mention the two components, but it has coefficients involving, these are roughly speaking coming from the Chern numbers of arbitrary degree. So it's some huge elaboration of what we already know. But right now, this is still some kind of dream, and I can talk a little bit about how to do it rationally. And the goal is to eventually get there, and we will see. We'll see if we can. We're certainly not going to get there at the end of this talk. I just want to say, this is a long-term process. Okay, in practice, what happens? In practice, moduli spaces of curves are not manifolds. They are so the issue has to do with this fact that you can have curves with symmetries, so you can have non-trivial stabilizers. So very naively, you would say that means that you have an orbifold, but actually, what it means is that the space of all maps, it's all smooth maps, you should think of as an orbifold, and then there's the Cauchy-Riemann equation that you're imposing. So you take some orbifold, and then you have a vector bundle on it, which you imagine to be like some kind of 1-0-1 form, and then this d-bar linearization of the d-bar operator some kind of section. So that's the naive picture. It's kind of hard to implement it in practice, but nonetheless, I will explain how this is. Say something about how this is done. But one way to formulate it is to use this language of derived orbifold, and I'm not sure this is what I might prefer term. I would prefer to call it Gromov space. But unfortunately, there's some kind of word has been used so many times, Gromov space, in the subject of symplectic topology that I can never remember what is the actual definition. as opposed to what I would want it to be. This word derived orbifold has been used by other people in other parts of mathematics, but not in symplectic topology, so I feel free to use whichever way I want to use it and not worry about any conflicts. But from my point of view, a derived orbifold is given by following data. You take an orbifold, smooth orbifold, and you take a bundle on it, which I call the instruction bundle, and you have a section. You have the section that's important. And you assume that the section has compact proper zero locus, and that's what you call proper derived orbifold. So this notion, it's analogous to what shows up in algebraic geometry, and we call it smooth derived stack. I think that's what it means, maybe also proper. And the analogy is basically like this. If you took this notion of derived stack, then locally you could describe it by something like this. But in algebraic geometry, it seems that there is more difficulty globalizing this description where there's like a single space and a single vector bundle on it. But in topology, we have more flexibility, and so we can define things like exactly like that. And in fact, there is a theorem of Hardin, which tells you that things are even more concrete than that. So you don't even need to know what an orbifold is, in some sense, because any such thing can be presented as follows: you have a compacting group. In fact, you can make the compacting group a unitary group. Then you have a smooth manifold on which this compacting group acts with finite isotropy, so that the quotient is orbifold. And then finally, you have a vector bundle, an equivariant vector bundle on this compacting on this G manifold, and the section, okay, whose zero locus is proper. So everything can be expressed, in terms of manifolds with compacting group actions, which I like to say it means that you could hopefully get a fourth year undergraduate or first year graduate student to understand the definition, which, as far as I'm concerned, is not the case for this quasi-smooth derived stack. Okay. So this is the context of this lecture. I'm going to be talking about Bordism of these objects and resolution to. So when people talk about Bordism of manifolds, first thing we need to do is think about structure. Of course, we can look at just manifolds with no additional structure, but that's not such a rich notion. So instead, similarly here. So I have this derived orbifold. I use this hideous notation with boldface x, and this curly x is the underlying orbifold. This T minus is the instruction bundle. Okay, this makes formulas much easier if you just think about that. And then what I'm going to do later is that the tangent space of this x I'll call T plus. Okay. So the tangent space of the orbifold, of the derived orbifold, I think is the formal difference between the tangent space of the underlying space and the instruction bundle. And in addition, you have this section. Okay. So what is a stable complex structure on such a thing? Well, it's a stable complex structure on its formal difference. Okay, now there is this virtual dimension, which is basically the dimension of curly x minus the dimension of this negative, which you should always imagine means that if you could achieve transversality, it would be the dimension of the zero locus. Okay. So when this virtual dimension is even, this notion of a stable complex structure can be expressed as follows: you have some vector bundle, or the full vector bundle, okay, on curly x, and then I plus and I minus, and then you have this isomorphism. So this isomorphism basically said, the way that I think about it is Tx, which is the formal difference, is isomorphic to the formal difference of I plus and I minus, which is a complex. So this isomorphism, of course, is just some kind of real isomorphism. There's no structure. Then you can say what it means for two stable complex structures to be equivalent. There's two procedures. There's two things to have in mind. Of course, there is you can change the isomorphism, and of course change I plus and I minus. Right? And then the next thing is the stabilization. So you can replace I plus by its direct sum with V, and I minus by its direct sum with the same vector bundle V. And you say that those two things are equivalent. Again, if you come from the world of derived stacks, you find these definitions kind of hideous because they think there should be some intrinsic thing. You could say just about the zero locus without do these actual models, but this works very well as well. Okay, and then of course, this definition should be special. I said derived thing. Well, if it's in the case where T minus is 0, there's no vector bundle, then this condition, this section is of course obviously 0, so X is just a compact orbifold, and then you can just specialize this and get the definition of a stable complex structure on the orbifold. So these are the objects that we want to study. It will, in a couple of slides, I will point out that actually there's slightly more refined structures that appears in symplectic topology, and that's what we're going to use. Okay, so we now have this notion of what it means to be a stably complex orbifold, subsequently derived orbifold, and we want to understand what it means for them to be equivalent to each other. And the only idea that you really need, the only idea is this notion of passing through the total space of a vector bundle. So let me just again explain. Everything here is fairly basic, except I use the term orbifold, but again, you don't need it. You can just express everything in terms of compactly, blah, blah. So let's say that we have a orbifold X, and we have a vector bundle on it. So again, that means you have orbifold total space of this vector bundle, which is again an orbifold. And if curly X is the ambient space, sorry, okay, of a derived orbifold, that means that you have this vector bundle T minus X. Okay, so you can pull it back to the total space of E, and then you can now get a new vector bundle on E. But what you do is you take the direct sum of T minus X with the pullback of E itself. Okay, so when you pass from curly X to curly E, you enlarge this space. So you need to enlarge the obstruction bundle. Accordingly, you enlarge it by the same value. You take this direct sum, and what you want is a section. So, well, you have a map from X to T minus X, so like pull back, you get a map. And also you can take the identity. So you call that, so starting with the derived orbifold curly full face X, you end up with a derived orbifold full face E. And the point of this slide is that you want to consider those two things to be the same. Why do you consider them to be the same? Well, roughly speaking, because if you look at zero locus and zero locus is exactly the same, and you just kind of cut out, but yes.
And open subsets contain.
Thank you. Open neighborhood of the zero. That's what I meant. Okay, so there's thank you. Well, you're reading actually. So you define equivalences of such objects as zigzags with the following operations. So 2 is what I just said, pass through the total space of the vector bundle, and 1 is you restrict to an open subset to an open neighborhood of the zero locus. So you take the zero locus, you don't want to change the zero locus. That's exactly why what's written there is completely wrong. If you don't want to change the zero locus, then anything away from the zero locus is not relevant to the structure that we're looking at. So we just take a small zero. In fact, part 1, you can, if I'm going to talk about Bordism, you can neglect it because you can take care of that by Bordism. Okay. Since I was trying to be very careful and define stable complex structures, again, both operations can completely induce canonically stable complex structures. So open subset, open neighborhood is obvious. To total space of the vector bundle. Well, this takes a little bit more work, but basically you can just, because you're adding the same thing to T plus and T minus, you can just pull back that plus and nothing changes. You just add the identity isomorphism to the isomorphism that you spoke. Okay, so that means that not only do we have a notion of stable complex structure bundle orbifolds, we have a notion of equivalent protection. Okay, so just building up. So now finally we get to this word Bordism. So I'm assuming people are somehow familiar with Bordisms of manifolds. So Bordisms of orbifolds work out exactly the same way. Orbifold with boundary is, instead of being local, being modeled after Rn times 0, 1, is modeled after a representation times 0, 1. So the whole point, the reason I rotate is just to make clear that the group doesn't act on this color direction. It only acts on B. This is kind of easy to see if you have boundaries, but what else could you possibly do? If you have corners, it becomes slightly more important to say that the group does not act on the direction that have to do with the corners, it only has to act on the direction having to do with anyway, that's the representation itself, the part that does not have any boundaries. Okay, so there's always more than one way of defining Bordism groups. This is maybe the shortest way. So I start with the derived orbifold X, and I want to ask myself, what is a null Bordism? What does it mean for it to be represented 0? And what it means for it to represent 0 is that you can find some orbifold whose boundary is exactly X. Again, curly X is not compact, and this bounding orbifold does not need to be compact. But what you need is to be able to extend T minus to a vector bundle on this thing whose boundary X, and this section to, again, this thing whose boundary X. And finally, you need this extension to have the property that is zero locus. So that's what it means to have a null Bordism of the derived. And same thing with stable complex structures. You have to be a little bit more careful. So when I was 2 slides ago, and I'm still here, I was lazy in this definition here. If you notice, I plus and I minus are complex vector bundles. So they're even. So the dimension is even. There's a difference between the dimension even. So this definition really only works when X has even virtual dimension. Okay, but in practice, if you want odd virtual dimension, you can just add a copy of R either to the left or to the right. Doesn't make any. It's basically the same notion. So that's exactly the same thing happens here. An algorithm of if you now have a stable complex structure on X, and let's say X is even, then an algorithm of a stable complex structure means that now you can extend I plus and I minus to this bounding manifold. And you take this isomorphism tangent spaces that I had on the previous slide, and you add a copy of R, and then you'd like to make sure the isomorphism extends. So again, it works out exactly the same thing as formula. Okay, and again, we have saying everything was a derived world, but you could do it without deriving anything, and you would get Bordism score. Okay, I'm going pretty fast. Okay, so now we have, finally, I can define what it is that I am talking about. Again, it will turn out that the main theorem will not quite be, but this will be small areas. This is a thing we should be thinking about, just for technical reasons. I will have to change the small thing. So, so now we can define a group. For every integer n, we have something which I call the or whatever, the derived orbifold coordinate group in dimension n. So this is some quotients. Quotient of what? A quotient of the group really generated by stably complex oriented derived orbifold. Stably complex of dimension n. So this dimension again means the virtual dimension. It means the difference between the dimension of the ambient orbifold and the dimension of the rank of the vector bundle. And there are 3 relations. So the first relation, as I said before, if you have stable complex structures that are equivalent, you want to mod up ahead. This is actually taken up by 3, as we'll get to it. If 2 things are equivalent, if you do it correctly, you can just deal with it by null Bordism, but nonetheless, I'm going to say it explicitly. Next one is the notion of equivalence orbifold, which again involves 2 things: restriction to an open neighborhood of the zero locus and stabilization. Stabilization you really need. A restriction to open neighborhood, again, you can absorb into 3. And finally, this 3 part, which is null Bordism, you kill in null Bordism. Okay, so this is some group. So the first thing that let me continue and then I'll go back to that. If we take these things and we restrict attention to orbifolds rather than derived orbifolds everywhere, which means most importantly, when we do null Bordism, we do not allow ourselves to kind of have this stabilization process. So we don't, we never involve derived orbifold. Everything is orbifold. We get something which I call, the orbifold Bordism group in dimension n. Okay, and similarly, if you now take orbifolds and not allow them to have any singularities, make them all manifolds, you get some classical group, which is a complex Bordism group, which was studied starting basically with Tom, and then Milner and Novikov proved the main results of the computation that I gave on the first slide. Okay. So we have these 3 groups, and it's obvious that we have these maps in them. The classical complex Bordism group that maps into the orbifold complex Bordism group maps into the divine. So the classical one we understand fairly well. I mean, there's like a whole, branch of mathematics, maybe algebraic topology, whose job is just to think about this group and things that are associated. Anything that if you ever hear words about chromatic homotopy theory, that's basically taking the complex Bordism group and complex Bordism theory and localizing it, completing it at prime P, and then taking out some summons. Anyway, it's creating some construction which is think I was just basically studying this group. And the rest of these are not so well studied. I mean, the issue basically is that I've been hiding from other things. When I say orbifold, I don't mean effective orbifold. And analyzing these groups, mostly is when people have tried to do it in the effective case. And this one, well, I'll make some indication later, but there's basically very little benefit in the research. Now, again, this first one's computed, the second one we don't understand. The third one, the first thing that I want to say about it is that unlike the first two, it's not necessarily the case that n is a positive integer. Okay? So these groups are non-trivial in negative dimension as well as in positive dimension. Again, the last one. And the reason is very simple. You can just have I said you can have this manifold and the orbifold, the vector bundle on it. The orbifold can be like point mod G, okay? And the vector bundle can be any representation with no invariant subspace other than 0. Okay, and if you consider that vector bundle as vector bundle over point mod G, you will see that it has negative virtual dimension and that you cannot basically move things off of so you get things in negative I said homotopy in negative degrees now. Since the word slipped out of my mouth, I said homotopy groups. It turns out that I defined it as some quotient by some equivalence relation, but one can show in fact that there is essentially a topological space of which these are the homotopy groups. But let me not do it. Okay. So in principle, the one way to kind of
You said it's not very negative real and you said
yeah, that's right. There's a topological space for these two, and then this one, the last one, there is a topological space up to some J.
the definition of null Bordism.
Okay, I can go back here. So null Bordism. So I have X, which is an orbifold. So null Bordism is an orbifold with boundary X. Okay. Now X carries a vector bundle, the instruction bundle. The instruction bundle should have an extension with its null Bordism. Okay. And X also has a section. And that once you extend the vector bundle, you should be able to extend the section. You have an extension of the section that's triple. You have to choose all three of these things. That's a null Bordism. And the only condition is that the zero section of the extension should itself be proper.
If I have some right and degenerating it, then the null Bordism is basically the list of the obstruction module of whatever moduli is on that class.
Well, in most things are not going to be. Algebraic geometry, most things are not going to be null Bordism. I mean, in order for them to be null Bordism, that's a very strong homotopical assumption. Like, no Riemann surface other than the elliptic curve, the connected Riemann surface, other than the elliptic curve is null Bordism. Because the first term class detects, it gives you an obstruction. This is in the classical thing. And the Bordism, same thing here. And in fact, the consequence of what I'm saying is that even as a derived orbifold, you cannot. Okay. I cannot tell what time it is. It's really disconcerting. It's okay. I don't know if I'm going too fast or too slow. I'm probably going too fast. That's sure what's happening. Okay. Yeah. So anyways, these are the groups we should be interested in. And part of the reason you should be interested in is because they make some non-trivial link between the stuff that people with Gromov-Witten theory or some stuff with topology study and people in other areas of topology and homotopy. Okay, so just a few words about some kind of local geometry that will be useful for the next slide. So from the definition that an orbifold is locally modeled after a representation of a finite group. These charts, which are basically V, gamma, V is the gamma is a finite group, and V is the representation of it. So now, if I look at this, the representation of a finite group, then the total space is stratified by the stabilized group. At every point, there's a group stabilized, and that gives me some decomposition into closed, into locally closed. So now, in an orbifold setting, you have to be a little bit careful because it's not actually the group that matters, only the opto isomorphism. I'm going to just not worry too much about that. There is some adjacency of strata, which corresponds to inclusion of groups, but actually maybe conjugate conclusions that differ by inner conjugacy you want to consider to be the same. So again, a small issue there. But there's the key important thing is that there is a stratification, geometric stratification that is related to just representations of finite groups. Okay. Okay. In the derived cases, yes. Yeah. Okay. In the derived case, you have additional structure, which is that not only do you have this representation that's kind of how the group acts on the space, okay, but you have a point which is fixed by some group gamma, so and then you have also this vector bundle. So the fiber of the vector bundle at this point now becomes another representation of this group. So what you have is pair of representation, B plus and B minus. That's the thing that labels the geometry. You should think of this as some kind of virtual representation. When you stabilize, I didn't say it here, stabilize, the obvious thing that happens is you add the same representation to B plus. So, because this is maybe not so much something that I would say, well, it is still representation theory of finite groups, of course, but not exactly the kind of thing that we discussed in the first course on the subject, but that's what's going to show up in a second when we start doing refining our structures a little. So the next slide is the reason I have introduced this one. Okay, so finally I can say it here. So this was proved by Clean, Smith, and I a year and a half ago, I guess. I have no sense of time, so it feels like I feel like 5 years ago. So what did we prove? If you take any closed symplectic manifold and you equip it with an almost complex structure which is compatible with the symplectic form, then you have these moduli spaces, M bar G N, okay, of X comma G beta. Moduli spaces of genus G curves with N marked points in a given homology class with respect to this almost. And what I want to write is that this moduli space is a stably complex derived orbifold. Now that doesn't make sense because this moduli space is just some compact cluster of topological space. So what that really means is that you can construct the stably complex derived orbifold so that when you look at the zero locus, which is some kind of Orbi space, okay, you get this. You get that one. That's it. And I just abuse notation and then just put this in parentheses. Now, the fundamental, okay, you could imagine sometimes you can do this for any topological, for any space. If somebody gives you a compact topological space, you can just produce some smooth manifold and vector bundle, and in fact, you make the Rn if you want. Whose zero locus in a topological space, that's not very helpful. The essential thing is that the construction, is kind of canonical, doesn't depend, and the underlying Bordism class does not depend on the complex structure. Okay. And maybe I should also say, if you were in a situation where transversality held, where we didn't have to go through all this derived stuff, it would agree with the Bordism class as obviously defined by geometric construction. So that's the theorem that justifies me talking about this work in this room, because the idea is that once we have a result like this, we can start to use it to lift all the structures that we have, all the operations that we have from the world of ordinary cohomology to this world here. And if we want to do that, then we better understand this group better, because currently we don't. Okay, and now I wanted to say a little bit more, which is that these moduli spaces, they have a little bit more structure, and I'm going to use that, which is that, as I said, there is a stratification, and I've been talking about something having stable complex structure. But in fact, if you look at this, if you look at the stratification and you look at the normal direction of the stratification, you don't need to stabilize anything. The normal bundle along each structure already has a complex structure without adding anything, and that makes life quite a bit easier. I think this is not necessary, but I'm just putting it here for honesty's sake. So there is some additional refinements, and then I'll write more here for it. You can put this that we have this normal complex structure to all the structures instead of just this stable structure. Okay, so now we know we're talking about something concrete, even though we still don't know yet. Now comes the main result. So I say I take the ordinary complex order group studied by Tom and Miller and Novikov, and it maps to the one for normally complex orbifolds. Okay. So you assume the orbifolds. Okay. And then you'll have the derived version of it. These are the inclusions that I mentioned earlier, except that I added the superscript for this normal structure. And the statement is that both of these maps. And the way I stated it, because I said something about this normal complex structure, this has, in some sense, has very little, it's not special to complex cobordism. Yeah. So this omega n could have been, unoriented cobordism, and this thing could be unoriented orbifolds, but with complex structure and normal complex structure for all the strata. So there's no orientation inside, and none of the strata themselves are oriented, but in the normal direction, you have this complex structure. And similarly for the derived. Or I could do it for oriented cobordism, same thing.
If I take just the point for G, where G is finite,
yes.
Does it go to the point?
Yes.
On the left?
That is one choice. You could also send it to 0. There's a lot of choices. And in fact, in our paper, we discuss at least some natural choices. And you can easily send it back to the direct sum over, you can send it, when you split it, you can factor actually the map from here to here through the direct sum over basically all finite groups acting on sets, okay, which is basically going to measure the generic stabilizer group. So you can factor to that and then project to omega. So that part is relatively common. Okay, so as I said, this theory works for ordered cobordism and for oriented cobordism, for unoriented and oriented cobordism, and the correct generality of the result is that anything that lives under complex cobordism will have it. Okay, but except for the complex cobordism case, I'm quite sure that this normal complex structure is essential. By that I mean, if I didn't have this normal complex structure, and if I interpreted this to mean oriented cobordism, then I know that this map has kernel. If you just take the map from oriented cobordism to oriented orbifold cobordism and don't impose this normal complex structure, then the map is not injected. But that's, you can just prove it, you can just, in fact, the kernel of it is exactly the torsion in the oriented orbifold group, which we computed a long time ago. Okay, that's one statement. But of course, the statement, I'm giving some kind of simplified version of the statement. And there is kind of much more to it. One way to say this to people who don't do stable homotopy theory is to say, this is a statement at the level of homology, and in fact, it's true at the chain level. Okay, of course, that's not, there's no chain level. What it means is that one way to say this is that there is in fact a map of homology theory. You can look at manifolds mapping to a target X, and you can look at orbifolds mapping to a target X, and that there are groups associated with a topological space X. The functorial is satisfied by a torus for each one of these 3 slots. Okay? And for each one of these 3 slots, there is, and for each map, there is splitting, and the splitting is functorial with respect to maps of topological space. Okay? So it's very strong result for homology, and if you do a little bit more, you can even say it in the world of spectra if you want to make homotopy happen. So it's just a shadow of a more elaborate structure. Okay. Good. Okay. So now I just want to talk about how we prove this. So that's the other part of the title, resolution of singularities. So basically the paper came about because I was at Columbia sitting in the algebraic geometry seminar in 2009, just before the pandemic. And Dan Abramovich came and he gave some lecture about some cleaner, faster version of resolution of singularities. And then it occurred to me that if you can do this, then surely you should be able to use it in to study just not just algebraic varieties, but also it's also in kind of form. So this the method is basically like do a bunch of read some algebraic geometry literature and physics, except for one place where instead have to use some method of Fukaya and Ono, which seems to be doesn't have an analog in other parts of it. But I will explain. So the first splitting is the one that goes from orbifolds to manifolds. And this is really well studied in the algebraic geometric literature. They even have names for it. That is, you can do it in two steps. First step is alienization, and the second step is what we call desaccharification. It's really ugly. Okay, so if you have a representation B of a finite group, you can define some term like the non-abelianness of it. I don't know if that's a great name. So it's the rank of the maximal subrepresentation, which does not have rank one summit. Okay. So the largest piece of it, with the property that there's basically no characters that are included. And the basic thing is if you log on the origin and you look at all the new fixed points that you get on the projective, the exceptional divisor, and the exceptional divisor is an action of the group gamma, then this number will go down, strictly go down, unless of course it was RDD. So this is like, I mean, of course we all know that resolution sequence is very tricky, that if you try to do something too naive, you'll end up with some cycles, but that doesn't happen here. It's a very simple measure of complexity. You don't need to be Hironaka to imagine it. Very simple notion of complexity that just makes things simple. So if you apply it, and you keep going, you keep going, and you keep going, what you end up with is a bunch of things, one-dimensional representation. What you end up with is only one-dimensional representation in the V will cover the direct one-dimensional representation, which means basically that you have a map from gamma to some abelian group, and that all the non-abelianness is in the kernel, so that so that you don't see it from the point of view of the orbifold, because as I said, the orbifold is stratified by this generic stabilizing type. Okay. Okay, so that's the first step, and the outcome of this is what something we call the geometrically abelian orbifold, which means that again, in principle, it has this non-abelian part that's living generically over every point, but you don't see it in the quotient singularity. The quotient singularity is just the abelian case. The abelian case is basically something like a toric case. I mean, it's a very special type of toric case, and it's very standard how to take a toric thing and resolve the singularity and make it smooth. So that's the second. That's the completion of this first splitting. So the first splitting shouldn't be too surprising. If you want to implement it in algebraic geometry, as I said, it's built to know. If you want to implement it in differential topology, then you have to do just a little bit of work, because blowing up almost complex manifolds is not as straightforward as you would guess at first, because you don't have charts and things. You don't have nice nomenclature. But it can be done. So that's the first thing. So the second thing is what I said is quite a bit harder. So the first part is we have to do two things. First, you have to use Fukaya and Ono's notion of normally complex perturbations. So this is an idea that Fukaya and Ono had. I'm trying to count years, 27 years ago. So when at some point in the late 90s, they solved the Arnold conjecture over Q, and then they wrote some paper, very short paper, with some ideas about how they could do the same thing with integral coefficients. But at the time, the amount of technology that's required to implement that idea seemed to be like beyond what would be reasonable for a human being to do. So it didn't go much further. In around 2010, Greg Parker revisited their ideas and kind of wrote quite a bit more about it in the setting of exploded manifolds. And then more recently, Bai and Chu kind of using this kind of perspective where you can take moduli spaces and present them in some natural way, differential geometric way, as quotients by compact Lie groups. They decided to again revisit Fukaya and the Parker thing, and realize that it's much easier to do all these constructions when you're working globally, when you're working with a compact Lie group action, rather than when you're working locally, one finite group. So anyway, so that's one ingredient. Okay, and I will say a little bit more about how it's done in the next. And the next thing is we heard about this resolution of singularities, except that You can't use the original version because the original version somehow does not have any functoriality properties. Why do we need functoriality? Because we're going to work chart by chart. Okay? We need to make sure that we have this orbifold. It's not a variety, but it has these charts which are modeled after groups acting on representation. And that is clearly an algebra. You can think of it algebra geometrically, but I'll explain exactly more precisely what it means. But whatever you're going to do, if you do some procedure in chart, you need to make sure that if you do procedure in adjacent chart, that it agrees on the over. And Leonardo's procedure, initial procedure, did not satisfy this property, as far as I understand, as far as I'm told. I have not tried to read the paper, but it was, there are functorial improvements. I think the first one in the literature is Bierstern and Millman. This is from 1997. Kolar wrote more about it. This is some book on resolution of singularities and characteristic zero. And then I learned it from yet another version from which country and Bulgarish cannot pronounce Polish. And so, what this allows us to do, in the first procedure, you have to do it, but what we will do is we'll take a derived orbifold and it will produce something which is just an Orbi space, something quite singular. You should think like this is stack. Okay? Delete bubbles, something like that. And I'm giving you some hints already. It's going to have singularities that are modeled after quotients of zero loci of regular equivariant terms. So we have B plus and B minus, their representation of the group. Okay, you can just look at like polynomials on B plus values and B minus. Okay, that's the equivariant polynomials. Okay, and okay, so you take such a thing, you look at the inverse image of zero. That's some singular variety in general. You take a quotient like gamma. That's the singular space that you're or space that you're producing. Okay, and then as I indicated earlier, if this is the output of the first procedure, then the second procedure needs to start with this and then turn it into second procedure, not resolution. Turn it into an orbifold that is get rid of the singularities that are not themselves, that are not arising from taking the quotient by the group. Okay, and that's what the second step does, and because we go chart by chart, we need to be. Okay, so let me be a little bit more precise. So the main player in this Fukaya Ono story is this variety of this is basically like a vector space, but it's still a variety of polynomials of degree D from B plus to B on B plus with value in B minus. Okay, and it depends clearly depends on the integer D. If D is too small, there's basically nothing. As D becomes bigger, there's more and more of them. And if you take there's an evaluation map. Of course, if you take a point in B plus and a polynomial, then you can evaluate the point in B minus. And now comes the fundamental, some basic observation, which says that if you choose B to be large enough, okay, and you choose point B minus to be generic, then assuming that B plus is faithful, eventually this is inverted. This is just some kind of the usual proofs go along the lines of like there is if B is faithful, then there is some power, some tensor power. B plus is faithful. There's a tensor power of B that includes the regular representation. And then once you have that, then you have everybody else. But roughly speaking, it's like it's basically about interpolating, being able to choose interpolate. Being able to choose a polynomial that interpolates between the values of different points in the orbit of an element. Okay, so of course the way I stated it, this just suggests what you should do. You don't, in this condition, is not enough. Ensuring that this map, choosing D to be large enough so that this map is a subversion of the generic one is not sufficient for the rest of the machine to go through. But it gives you an idea for what you're supposed to do. And in practice, what you're supposed to do is you're supposed to look at each stratum of B minus, and then look at each stratum of B plus, and then ask yourself, what is the representation theoretic obstruction to transversality. And the representation theoretic obstruction to transversality is always something of the form, do the irreducible representations that appear in the source, and on the target, do they agree? That's it. So now, if you, mod out by this obstruction, if you look at the part of the obstruction, it's 0, which means if you look at the, oops, really want to update. Right. Okay. If you look at the, what was I saying? Yes. If you only ask, so you look at points in G plus, where stabilizes group is some kind of gamma prime, okay? And then you look only at the part of D minus where the stabilizing group is also, and the representation type of this gamma prime is some, let's say, some W. And you look at D minus where again it only has the same irreducible pieces, then the same result will hold if you restrict to these stuff. That's the correct kind of transversality if you want some kind of stratum by stratum transversality. You want to ensure submersion for every stratum into the correct target, because otherwise you just won't be able to hit it anymore. Okay, anyway, so you have this evaluation map, and if you pick large enough, you can pretend that it's then what you do is for each polynomial, you have a 0 locus in G plus, you have the inverse image of 0 and D minus. Let's call that 0 of D, and you take the union of them over all D. So this lives over the space of all polynomials. And now I get to use resolution of singularity. So I can say by one of these functorial algorithms, there is a resolution of singularity of the space. Let's call it 0 tilde. Okay? And because I chose it to be functorial, it's going to happen that if I were to restrict to some smaller subgroup gamma prime, it will be the same resolution. That's somehow continuous. Okay, once I know what is my proposed universal resolution of singularity, this is still entirely the world of algebraic geometry. Now finally we want to feed it into the differential topological context, which means I want to say something like orbifolds. So how do I do it? If I have a stratum where the isotropy is modeled after this data, which means after this B plus and B minus, which means B plus is what's happening in the ambient state, and B minus is what's happening in the obstruction level. Okay, then I have some point where there's some section S. Okay, it's arbitrary, maybe smooth arbitrary smooth section. But what I can do is I can deform it near the stratum so that it's given by a map to the space of polynomial. That's the thing that I can. That's the content of this proposal of Fukaya and Ono, which is kind of elaborated upon by Parker. So it's given by this map. And now our contribution. I mean, of course, this is not exactly how they said it. Okay. Our contribution is to say, well, once you have the fact that locally your map is given, your section is now being deformed so that it's given by the map to this space in the normal direction by this fundamental map. What you can do is you can require for the stratum to map transversely to the projection from the resolution of singularity into the space of polynomial. And well, keep it most transversely, then you take a fiber product construction, and now you pull back, and you don't have any singularities in the pull back. So that's the basic idea. That's how resolution of singularity ensures this construction. Okay. So I think I did run quite fast, but well, no, not okay. I just want to mention a few open questions. So the first one is whether there exists a multiplicative splitting. So I said there is a splitting, which means splitting of abelian groups. In fact, it is a splitting of modules over complex coordinates. So it has some structure. But in fact, every one of these groups that I mentioned, whether the orbifold Bordism group or the derived orbifold group, they form a ring. Okay? And we do not know whether these resolute. I mean, no. We know that our procedure is not compatible with multiplication. And that's for a very reason is because if you take two singular varieties, just like with an isolated singularity, and you take the product together, then the product does not have an isolated singularity anymore. Okay? But it has two strata, which meet along the deepest point, which is where where it's singular on both factors. And any procedure, and any the usual procedure for resolution of singularity, what they will do is they go to the deepest point and they do something. You have to figure out how to measure the deepest point. But in the case of a product, it's not too hard to measure. You go to the deepest point and you do something there. Well, when you do something there, that's not a product resolution. So that's so that's it's kind of hopeless to imagine that some geometric approach as one we're taking will work in complete generality. That doesn't. I'm quite optimistic that in the case of moduli spaces of pseudo holomorphic curves, we can formulate something that works more generally. But the procedure doesn't the geometric procedure is not. Now, of course, this kind of question is like tailor-made for homotopy theorists to answer. Their job is to find invariants preventing things from splitting. There's lots of them. Of course, they're just the product itself, but higher operations usually would be prevent it. But the groups are not sufficiently, current is not sufficiently well understood to kind of know where you would look. But on the other hand, what I said about where the geometric obstruction to our procedure being multiplicative also suggests where you might start to find these things. Okay. So that's the first thing. The second thing is, we've split this thing, which means in principle we now know a small piece of it. We know that the classes cannot go to zero, and we know that there is a lot more that we don't know. And we could dream to be able to compute the whole thing. And to me, being able to compute the whole thing is tied actually to this question. Instead of giving a conjecture about the structure, this is actually the essential question, which is here's a natural way of producing kind of a derived orbifold. So you start with you start with a compact manifold, let's say with a compaction relief group, which basically means to take with an actual orbifold. And now you have two vector bundles on it. Yes, but some stabilizing that's understood. And you have now two vector bundles on it. And now you look for a map between them with compact zero. So no. It's an equivariant smooth map of vector one. Yeah. That's right. So this is an example of a derived. The reason that this is something that you feel like is accessible is because compact manifold with a finite group action, that's the complex, that's a complex Bordism group, that's equivariant complex Bordism group that people could try to compute. And this is adding B plus and B minus is just some kind of doing some kind of Gromov-Witten construction over it. So in principle, these groups, there are tools to more directly try to compute them. So another way to think about what I'm asking is, maybe I have to go back to the beginning. I want to go back to the beginning. There is a splitting of orbifold Bordism into derived orbifold Bordism, and I'm saying to what extent can we write derived orbifold Bordism as a direct sum of orbifold Bordism group with extra data? That's the thing that actually algebraically write it down, but I didn't say geometrically it's given. So that's the next thing. And then the another direction which I really don't know what to do with is I said everything that's under complex cobordism, this works very well. You could work with oriented bordism or unoriented bordism. But the thing that I don't know how to do is when we're not under complex cobordism. And for example, this for this main case. If you're in a situation where you're hoping to get some kind of a roof genus and some interesting invariants in that direction, and you want to extract it from one of the derived orbifolds, it's not obvious because we'll do some blow-up procedure that will destroy, a priori destroy the existence of the space structure. But it's possible maybe that if you analyze things more carefully, try to understand exactly how the space structure interacts with the stabilizing group, you can identify some conditions under which, some more refined conditions under which you can do this. Okay, that's the end of my talk. I was planning to say let's see you in 10 years, but apparently only 5 years, and Maxine's not here, but have a great day.